Hi, welcome to the Mathemagic channel. Today we look at how we can understand the domain and the range of functions better. This will be a 5-part video, pretty straightforward and not super complicated. In the first part, we'll look at how we write intervals. In the second part, we'll look at what continuity and math errors are. In the third part, we'll look at what a domain actually is. In the fourth part, we'll say, hey, what's the range of a function? And in the fifth part, we'll look at some examples with Desmos. If you're ready and this is troubling you a little bit, make sure to click the like and the subscribe button first to give us a little bit of support, and let's watch the video. So how would we go about writing an interval? Well, here's the first example. Imagine that x is between 1 and 5. Now we call this inequality notation, which can be useful sometimes as well. Well, you can write this as x belongs to the open interval 1 until 5. And notice that we're using rounded brackets here. And the rounded bracket is there to indicate that the value 1 is rejected and the value 5 is rejected. And so we're going strictly from 1 to 5, not including the boundary. So strictly bigger than 1, strictly smaller than 5. Just like we had strictly bigger than, strictly smaller than before that. Now the euro sign here, that means belongs to. We find that in Venn diagrams. You could also add to this that x is a real number. So you can say x belongs to, and then this funky r that you've seen a few times in mathematics, the double long-legged r. That means all real numbers. Essentially, that is the same thing as saying that x belongs to negative infinity until plus infinity, which is all the numbers that we know, except of course for the complex numbers. But assuming that we haven't studied those so far, we'll just say x is any number that we know. Now, in contrast to this, you could have something like x is strictly bigger than 1 and smaller than equal to 5. And notice the change in how we write the brackets when we do that. We'll say that x belongs to 1, rejecting the value 1, because remember it's strictly bigger than 1, and 5, but here we're going to use a closed bracket, what we call a rectangular bracket or a square bracket. So a closed bracket at 5 to say that we accept the value 5. So 5 will be a value that x can be equal to 5. And that's what's important here. And of course you can specify that x is a real number just like we did previously, or you can just say x belongs from 1, the interval 1 until 5 included. So that's the difference between smaller than equal or strictly smaller than. So now if we saw an expression like this, and don't freak out, okay, this is not the end of everything as we knew it. It's just a little bit of mathanese. And so I'm just going to write this expression out, and let's see if we can figure it out together. So here, and we're going to put a comma and say that x belongs to r, and I'm going to close this. So this looks a little bit like a long sentence. It's a mathematical sentence for sure, and it could go a little bit like this, and I'm going to go item by item. The domain D is equal to, and then this kind of funky squiggly bracket here means the set of numbers. So the set of numbers x, and then that vertical slash means such that, means I'm going to describe how x is. So I'm going to say we're talking about those x's which are, and then x belongs to the interval from 1 to 5. So here we can see that we accept the value 1 and we reject the value 5. So x can be any number between 1 and 5, including 1 but not including 5. And then comma, x belongs to r means x is a real number. So if you're comfortable with this notation, well, that's very, very good, and this is how you can write intervals. Just one little point to add, you can add multiple intervals. So you could say, for example, you could write something like this: 1 until 5, union 6 until 7, and this would mean we go from 1 to 5, rejecting 1, rejecting 5, and 6 to 7, rejecting 6 and rejecting 7. So union here can, the vertical U that we use in Venn diagrams, can be a thing that we use to describe multiple intervals. So now let's talk a little bit about continuity and math errors. So imagine you assigned a function f of x. Now this is not going to be a very rigorous function, but let's just imagine that it's a little squiggle like this, and then suddenly there's a gap in the road and the squiggle keeps going on. So let's just say at the gap in the road, I'll make a little circle here and say that there's no value of the function. So the function doesn't actually have a value here. So to say that when we get to that little gap, if I put in an x value, the function doesn't return a y value because it doesn't compute and there's a math error. So what we talk about here is we talk about discontinuity. We say, oh, f of x is discontinuous at that point. And so the problem with a discontinuous function is that you can't quite study it. All the nice things we'd like to do when we study mathematics, finding the area under a curve, finding the gradient of a curve, well, we can't do any of this here because there's no curve. So simply speaking, when we look at continuity, we're looking to see where the curve exists. And so one of your jobs when you study functions is to say, okay, well, the curve exists here from A until B, and then maybe the curve exists here from C until D, and now that I've said where the curve exists and where it is continuous, then I can study it. Now the idea of continuity is that you could put your pen on a piece of paper and draw the curve without lifting your pen. Now initially I couldn't draw this whole function with my pen on the paper without lifting it up because there was a gap in the road. But now that I've said that the function goes from A to B, so I can say it goes from the interval, let's say A to B, and the interval C to D, I've successfully said that this is where the curve exists and I'm allowed to study it. So let's talk about math errors and how this is related to continuity. At the initial level, when we first learn about domain and range, there are two math errors which are quite common, and so we're going to look at those now. So the first one is this: like if you do 0 divided by 4, let's say you have no candy and it's Halloween and you have 4 friends showing up at the door. You do 0 divided by 4, well, everybody gets no candy and it's a sad day and everybody goes home empty-handed, and that's fine. So we're taking the number 0, dividing it into 4 bits, remembering that division is the process of separating into equal parts, and we're okay with this. Now if, however, you did 4 divided by 0, and so 4 divided by 0 would be like I have 4 candies and I'm going to split this into no friends. Well, the process of division is of separating into equal parts, and separating into no parts is not a thing. So if you do this, you're going to stick that into your calculator and your calculator will explode. You're going to get a math error. You cannot divide by 0 in mathematics. You need to divide by something. So division by 0 is a math error, and we're going to say that that's the very first one that we need to understand. Dividing by 0, that's a big no-no. You can't do that in mathematics, and therefore whenever you have that situation with your function, you might have to reconsider where you have a curve and where you don't have a curve. Now the second most common math error that we learn, well, let's just think about this for a second. If I do 2 squared, which is 2 times 2, I get 4. If I do -2 and I square it, I get -2 multiplied by itself. Remember, the process of squaring is to multiply by itself, and I get 4. So in both cases, when I multiply a number by itself, it turns out positive. So whenever I square something, it always turns out positive, which is really good, and it's quite useful sometimes. So what happens when you're faced with the reverse operation, which is square rooting? And imagine you're faced with the question, find the square root of -4. And well, that's a bit of an issue in the real numbers because we don't have a number multiplied by itself that's going to give you a negative. So it's actually impossible to find the square root of a negative number in the real numbers. Of course, we've created a whole number system called the complex numbers where this has solutions, but in the real numbers, and for now, we don't have any solutions. So the square root of -4 is going to be a math error, and whenever you plug that into your calculator will return error or undefined, and it'll tell you that the square root of negative numbers is not actually a thing. So this is another thing to think about, square rooting. So square roots of negatives. So square roots of negatives, you can't have that, and when you do, negatives, oh my, negatives, square roots of negatives, that's no good, and we're going to say that that's a math error. So let's see how that's affecting functions and how we draw functions. So if we go ahead and draw an x and y axis here, so labeling this as the x-axis on the horizontal and the y-axis as vertical, and we're to draw a little squiggle on this x and y axis. Now currently we can't really say, even though I could call it f of x, we can't really say that this is a function because we haven't assigned a domain yet to it. So there's some important things to do before we decide that a function is a function. We should first say that it's well defined, And so well-defined meaning that there's a domain attached to it, so we know where the function actually lives, where does it go from, and where does it end. And we need to make sure that functions are what we call one-to-one. So one-to-one means that you get one value of x for one value of y. So typically when you see functions, you always see one value of x which gets assigned to one value of y. And if ever you have a function that loops onto itself, so a function that might do something like this, for example, where for one value of x, you get two values of y. So let's say you get x1 and then you get y1 and then y2, which would lead you to having point coordinates like x1 and then y1 and y2 like this, which is not something that you see very often. Then you can say that this is not a function. So you're not allowed to have functions where you have two values of y for one value of x. So it should really be that the function has one value of x for one value of y. And the third criteria for a function to be a function is to say that it needs to be continuous. Now it needs to be continuous not just anywhere, it has to be continuous over the domain. So if you've assigned a domain for your function and you say it goes from here to there and it's continuous over that domain and it's one-to-one over that domain, so in other words it's well defined, then you can study the function. But at a certain grade level, before you've checked that it's well-defined, one-to-one and continuous, you're not really allowed to study the function yet. You have to wait until these three criteria are met for you to say that, okay, we can start studying it and doing stuff, finding solutions, differentiating, whatever you want to do. So simply speaking, here, what is the domain of this function? Well, let's say that this function starts at some x value a and finishes at some x value b here. We could say that the domain of this function, so d, is equal to the number set x such that x belongs to, and you could say the interval a until b may be accepted or rejected. We're not sure because we haven't said whether it's, whether these values are accepted or not. So here we're saying rejected. You would have to check in your specific question if those values are good or not. And x is a real number. And so what I've done just now is I've created a set of values for x to say I'm only going to study x's from a to b here, because outside of those two values there's no curve. So essentially, what is a domain? Well, a domain is where we have a curve. So you could simplify it as the values for which the function exists, or you could say where does the curve live, or where does the curve exist? Or in mathematical terms, you could say where is the curve well defined, one-to-one and continuous. And so here you see we've decided we're only going to study this curve from a to b, which is here, and outside of this we're not going to study the curve. And as long as we stay between a and b, then that's good. The curve is everything we need it to be, and that's the domain of the function. So simply put, the domain is where the curve lives. Okay, so I hope this is helpful. So now if we look at a similar curve, let's say that goes like this, and we say this is f of x, you'll notice that this f of x here has a low point and it has a high point. And so if we look at this piece of a function here, or this little section, when we talk about the range of a function, we're talking about the y values, like how low does it start from until the maximum value. So what's the lowest value of y that it takes, and what's the highest value of y that it takes? So if we were to say that this function goes from a height of a to a height of b, we could say that the range of the function, so this is the range r, but not to be confused with the double-legged r that we did earlier, which meant real numbers. The range of the function is equal to, so the set of numbers y, such that y belongs to, and we could say, let's say this time that we accept the value a perhaps, so accepting the value a, so greater than equal to a, and strictly smaller than b, and end of set of numbers. You could also say y belongs to the real numbers. You can do all that as we did earlier. A lot of the times it's not really a big deal, but this is fine. Just to say y belongs to the interval ab is kind of okay. If you don't say that it's a real number, we imply that it's a real number. So yeah, I mean, the range of values is the low point to the high point, so it's the low point, so the lowest point of the function until the highest point. So, and if the highest point is plus infinity, then you just say that, right? So if a function goes all the way to plus infinity, then you can say the high point is infinity. So if in my drawing perhaps I drew an arrow instead to say that the function just keeps going up and up, then here you could say something along the lines of the range is equal to the set of numbers y such that y belongs to, so we're going to say starting from a included all the way through to plus infinity, and infinity always takes a rounded bracket purely for the fact that plus infinity is not an actual value, it's a concept. So whenever you use infinity, make sure you use a rounded bracket. If you were to just write it as inequality, you could say, because you can do that too, you could say y is such that y is greater than equal to a. These two statements are exactly the same. So you could also say that. You could say we're looking at the y values such that y is greater than equal to a, which implies that it just keeps going on and on and on. And so this is inequality notation, whereas the first one is interval notation. So let's think of two good examples of functions to study here, which we're going to look at with Desmos after this. So the first one is going to be f of x, and this function is going to be defined as 2 plus 1 over x minus 3. Now remember the two types of math errors that we had. The first type was a zero divider, and the second type was a negative square root. So in this case we see that when x is equal to 3, so if we were to say x is equal to 3, well, y is going to be undefined. It's going to be a math error at 3, because when you do 2 plus 1 over 3 minus 3, you'll do 1 over 0, and 1 over 0 is no good. It's a math error, and therefore there's no value of x. So you can just imagine that there is no function, so there's no curve. Actually, f of x doesn't actually exist. Does not exist, right? And does not exist at x equal 3, for x equal 3. So when x is 3, you'll have no curve. So you could think about it like a squiggle, and then there'll be a jump at 3, and then the squiggle will resume. So there's values. For any other x value, it's fine, but at x equal 3, there's a math error, and there's going to be a problem. So we need to assign a domain to this to make sure that the function is well-defined, one-to-one, and continuous, so that it's continuous over the whole interval. So we can do that, and we can say the domain D is equal to the set of numbers x such that, so here we can use inequalities, that's pretty helpful. We can say x is a real number, and be flexible with this kind of writing. You can just say whatever you need to say for it to mean exactly what you want it to mean. So you want to say that it's a real number, so any number is good, but we don't want 3, so we can say x is different to 3. So as long as x is not 3 and x is a real number, this function exists. And this is a fine way to write the domain. Another way you could write it is to say that x belongs to minus infinity until 3, rejecting the value 3, and from 3 to plus infinity. So you could do that. You could do two intervals, minus infinity to 3, and then 3 to plus infinity, and that would be fine as well. But this is more convenient for this one. Now, before we jump into Desmos, let's look at another example. Let's say that we have a function h of x here, and h of x is going to be equal to the square root of x minus 2. Now, we've already established that the square root of a requires that a has to be greater than equal to 0. So the square root of 0 is 0. The square root of a positive number is fine. The square root of a negative number is no good. It's a math error. So here's the issue then. The x minus 2 quantity here needs to be greater than equal to 0. And if we rearrange this a little bit, that simply implies that x has to be greater than equal to 2. In other words, if x is not bigger than equal to 2, you won't have a function. So if x was 0, for example, the square root of 0 minus 2 would be the square root of negative 2, which is a math error. So if you did h of 0, you'll get the square root of 0 minus 2, which is the square root of negative 2, and then that leads to a math error, and there's no curve. So simply put, this means that you could think of the curve as existing from the value 2 onwards. So there's no curve before 2. So if you were to write this on a number line, the value 2 is okay, and as long as you're after the value 2, so 3, 4, 5, 6, 7, you can do the square root of all these numbers minus 2 and you'll get an answer. But before the value 2, so you can think about 2 as a cutoff point, there's actually no curve. And so once again, we're going to use our skill to explain how we assign a domain to this. So the domain of this function is equal to the set of numbers x such that x is greater than equal to 2. So So you could say that. This would be a fine way to define the domain. Or you could use interval notation and say the domain is equal to the set of numbers x such that x belongs to, and so the interval is going to be from 2 to plus infinity. And this is a really good way to learn to write domains. So 2 including the value 2, because the square root of 0 is fine. Remember, at 0 we'll have, so when we do 2, we'll have 2 minus 2, which is 0. 0 times 0 is 0, so we accept the value 2. 2 exists. If you enter 2 in your function, you will definitely get an output. Until plus infinity, and remember plus infinity takes a rounded bracket because it's not an actual number, it's a concept. So we're going from 2 including 2 until plus infinity. These two statements are exactly the same. So whether you write the domain the first way or the second way, you've successfully written your domain and said that it's any number above 2, and that's absolutely great, including the value 2. So if we look on Desmos here at the red curve, which is the square root curve, which we've just discussed. So the red curve is the square root of x minus 2. And as you can see here, it starts from 2, so 2, 0, because when x is equal to 2, we'll get 0. And before that, we don't actually have a curve. There's nothing there. So if you were to think about, oh, what happens to this function at x equals 0, you wouldn't have anything because there's no curve. So you're not allowed to study it at 0 or 1 or -2 or -3 because there's no curve. But you can notice that from 2 to plus infinity, there's a curve. So that's where it lives, from 2 to plus infinity. It's 1 to 1, one value of x for one value of y. It is continuous. There's no jumps in the road here. From 2 to plus infinity, it's continuous. And it's well-defined. Well-defined meaning we've said it lives from 2 to plus infinity. Now, with that in mind, this is a function. As long as a function follows these three criteria, you can say that it's a function. If any of those are not met, then it's not a function. So you need to be careful with that. So now if we look at the second example here, which is the blue curve, so without the vertical asymptote, let's just think about the blue curve. So the blue curve is 2 plus 1 over x minus 3. And you notice that at 3, you'll have a 0 divider, you'll have 1 divided by 0. 1 divided by 0 is no good, we don't want that. So we're going to say that there's no function at 3. And because there's no function at 3, there's going to be a gap in the road and a discontinuity. So if you were to write your domain out, you could say that this function exists for all real numbers except 3. So any real number is good except when x is 3. So we just wrote that domain previously, and this is just a reminder of what it looks like, or some way to visualize it a little bit. We can actually draw what we call a vertical asymptote at x equals 3. So whenever you have a 0 divider, typically you're going to get functions which jump to negative infinity and jump to positive infinity, like this one. And even as I zoom out, we get very close to this value here at 3, but we never quite reach 3. There's no actual value for your blue curve at 3. It's undefined. So we hope this was useful to you. Please remember to like and subscribe to the Mathemagic channel so that we can keep putting out content to help you with your mathematics and get more subscribers so that we can increase our audience and have more people learning math with the Mathemagic channel. This is Domain and Range. If you have any questions, put them in the comments below. We'd be most happy to answer them. And good luck with this. This is the beginning of the studies of functions, so pretty important topic. Thank you so much for watching, and see you on the next one. Bye-bye.